In a gas-to-liquid shell and tube exchanger, how do you mathematically and practically determine the controlling thermal resistance? And how do you optimize it without destroying the hydraulic budget?
Well, to address your premise, specifying titanium without mathematically isolating the true bottleneck is a severe failure of resource allocation.
It's just wasting capital.
Exactly. It is the equivalent of expanding a 10-lane highway that immediately feeds into a single-lane dirt road. The thermal flux will not increase.
So how do you dissect it?
You dissect the one-dimensional heat transfer pathway by comparing the individual thermal resistance steps. You have the gas side convective film resistance, which is the inverse of the gas side coefficient.
Right.
Then you have the liquid side convective film resistance, the conductive resistance of the metallic tube wall, and finally the inner and outer accumulated fouling factors.
And you are looking for the maximum value there.
Precisely. You must identify the specific boundary layer or material layer with the largest numerical resistance value. That exact layer is your primary bottleneck.
So you only target that side.
Strictly that side. If you target the non-controlling side, the overall U value remains virtually unshifted.
Give me a real-world numerical example.
Sure. If I'm evaluating a gas-to-liquid compressor intercooler, the low-pressure gas-side film coefficient might be severely depressed, maybe hovering around 50 watts per square meter Kelvin.
While the liquid side is highly turbulent.
Exactly. The tube-side liquid coefficient might exceed 1,200 watts per square meter Kelvin. So the gas-side resistance is overwhelmingly the controlling factor.
So what is the optimized design mandate?
You add extended surfaces, specifically longitudinal or transverse external fins on the tubes, to artificially increase the heat transfer area strictly on the gas side, or you optimize the shell side baffle spacing.
Wait, let me stop you right there. I want the junior observers to understand the physical reality. You cannot just pack infinite fins onto a tube or tighten baffle spacing without a massive penalty.
You absolutely cannot.
What is the immediate, unavoidable hydraulic consequence of that geometric change?
The inescapable penalty is a severe escalation in the hydraulic pressure drop.
Because of the surface roughness.
Exactly. Adding fins alters the surface roughness and flow geometry, and decreasing baffle spacing physically amplifies the frictional shear stress against the fluid. Both strictly increase the shell side pressure drop.
And this is where the HTRI software traps people, right?
Yes. The critical failure point is blindly chasing a high U value on the software without verifying that the increased frictional losses actually fit within the plant's allowable hydraulic budget.
If the upstream compressor lacks the head to push through that new resistance,
then the thermal optimization is worse than useless. It actively bottlenecks the plant's throughput.
let us expand that multi-layer series concept. I want to move to high-temperature reactor vessels. How do you mathematically model the structural temperature gradient across a multi-layer refractory-lined reactor wall?
Well, the gradient is modeled by applying Fourier's law of heat conduction across a multinodal series network.
And I expect you to detail the boundary layer impacts here, which junior engineers always omit.
Right, they treat it as a pure solid-state problem. But first, the total thermal resistance is the linear sum of the individual layer resistances.
Which includes what, specifically?
The conductive resistance of the internal dense refractory layer, the secondary insulating refractory, the low alloy steel pressure shell, and finally the external ambient convection.
And the governing principle for the interface temperatures.
The interface temperatures are determined by ensuring the heat flux, the Q over A, remains strictly constant through each respective layer at steady state.
So the lowest conductivity dictates the biggest temperature drop.
Exactly, because resistances in series add up linearly. But, as you pointed out, the fatal oversight is neglecting the internal process gas convective film coefficient and the external ambient convective boundary layer.
If you assume the internal refractory phase is exactly at the bulk process temperature,
then you inherently skew the heat flux calculation. You will fundamentally underestimate the actual operating temperature of the steel pressure shell.
I don't just want the math. Ground this in reality. Walk the panel through a specific field application where underestimating that steel shell temperature causes a structural failure.
Consider the engineering of a cold-wall hydrocracker reactor. The design inherently relies on a dual-layer refractory system.
Usually a dense inner layer and an insulating outer.
Right. Typically a 150 millimeter dense erosion-resistant internal layer backed by a 50 millimeter highly insulating layer.
To protect the steel.
Exactly. The objective is to keep the thick, low-alloy steel pressure shell operating safely within a narrow design window, usually 200 to 250 degrees Celsius.
And what are the two opposing limits we have to check?
First, the outer skin temperature must remain below 60 degrees Celsius for personnel protection. Secondly, and far more critically, the internal steel face must remain definitively above the acid dew point of the process gas.
To prevent localized condensation corrosion.
Precisely. Now, if the highly pressurized, hydrogen-rich process gas manages to slip past the internal refractory layer.
Through expansion joints or stress cracks.
Right. It physically bypasses the designed conductive resistance. This gas slip creates a direct, localized convective hotspot against the bare steel shell.
And in a hydrocracker, exposing low-alloy steel to high-pressure hydrogen directly triggers what?
High-temperature hydrogen attack, or HTHA. The molecular hydrogen dissociates, diffuses into the steel lattice, and reacts with the carbon to form methane gas.
Which physically rips the steel apart from the inside.
Exactly, via microscopic fissuring. If those convective films weren't rigorously accounted for in the baseline thermal model, the reliability team might mathematically misinterpret external thermal imaging.
Right, they'll think it's a minor insulation flaw until a metallurgical rupture is imminent. Let's talk about fouling factors. I frequently sit in operational review meetings where process engineers instinctively blame fouling every time duty drops.
It is the ultimate catch-all excuse.
Exactly. They treat it as a guessing game. How do I know you aren't just guessing alongside them? How do you mathematically and dynamically isolate convective film coefficients from actual physical fouling?
Defaulting to physical fouling without data is just laziness. To isolate the variables, you must first express the overall dirty heat transfer coefficient as the series sum of the clean convective coefficients, the static wall conduction, and the transient fouling factors.
And you pull the operational overall resistance from the DCS.
Yes, it's simply the inverse of the dynamically measured overall heat transfer coefficient derived from the live DCS temperature and flow transmitters.
But how do you eliminate the guesswork on the clean side?
By not relying on static design sheets. I calculate the clean convective film coefficients in real time. I actively recalculate the Nusselt number correlations based strictly on actual live operating flow velocities.
You update the transient physical properties live.
Yes. Dynamic viscosity, density, and thermal conductivity as they shift with the live temperature. Once I have those real-time clean convective resistances, I subtract them from the measured overall resistance.
Leaving only the physical fouling resistance.
Strictly the accumulated physical fouling resistance. It mathematically isolates the true particulate buildup.
So you separate the hydraulic flow profile from the physical buildup. Quantify that. Give me an operational scenario where failing to make this distinction led to a costly error.
A classic high-cost example involves a shell-and-tube crude preheat train. The DCS suddenly registers a 20% drop in heat duty across a critical preheater.
And the shift team assumes the bundle is coked up.
Exactly. They assume a bad batch of crude caused severe coking. They trigger a panic response schedule, a costly bypass, order a specialized chemical wash contractor.
But your dynamic analysis shows something else.
Right. By tracking the real-time Nusselt correlations against the DCS flow meters, the analysis reveals that 15% of this total duty drop is strictly a thermodynamic consequence of reduced crude velocity.
Because the unit was in a turndown state.
Exactly. Lower velocity means a thicker laminar sublayer at the tube wall, which drastically suppresses the convective film coefficient.
So only 5% was actual fouling.
Precisely. The operational misstep is attributing flow-driven convective suppression to physical thermal resistance. Distinguishing the two prevents millions in unnecessary maintenance downtime.
And what about pleat and frame exchangers under these turndown conditions?
I apply an even stricter caution there. Plate exchangers rely entirely on inherently high turbulence generated by narrow, corrugated channels. They are profoundly less tolerant of operational fouling margins.
Because even microscopic buildup chokes the channel.
Exactly. A tiny layer of physical buildup combined with a slight loss of velocity destroys the shear stress required to keep the plates clean, causing the pressure drop to spike exponentially.
That brings us perfectly to the mechanical and hydraulic consequences of conservative engineering. Let us examine design margins.
The stacked margins trap.
Exactly. I see EPC engineers relying on stacked margin safety factors on top of safety factors to cover up a lack of modeling confidence.
It is a massive issue.
How do you specify the optimum fouling resistance allowance for a highly viscous residue exchanger without triggering these overdesign problems? Explain your philosophy on overdesign area margins.
Well, stacking safety margins is not conservative engineering. It is a severe detriment to plant operability. When a designer stacks a conservative fouling factor on top of a conservative heat release curve,
And then caps it with a 20% area margin.
right, they are engineering a physical failure. My methodology references TEMA baseline tables, but I heavily cross-reference those static values with real-world plant historical run data for the exact crude blends.
And what is your absolute maximum limit on the area margin?
I cap the overdesign area margin strictly at 10 to 15%, explicitly to handle known debottlenecking requirements.
I'm going to challenge you on that cap. If a client is spending capital and explicitly mandates a 30% area margin because they absolutely never want to fall short on duty at end of run, why refuse it?
Because I understand the physics of the boundary layer, and the client is often just looking at a commercial spreadsheet.
Are you not inviting a performance guarantee failure by refusing?
No, I am preventing one. Over-designing a bundle inadvertently but unavoidably lowers fluid velocities. This aggressively accelerates the exact physical fouling mechanism you are attempting to mitigate.
Because of the sheer volumetric flow area.
Yes, if you oversurface a heavy hydrocarbon exchanger by 30%, the extra flow area causes profoundly sluggish fluid velocities during the initial clean run conditions.
And if velocity drops below the critical shear stress threshold?
Say, below 1 to 1.5 meters per second for crude, the boundary layer becomes stagnant. High residence time mathematically guarantees accelerated fluid coking, and suspended heavy solids physically precipitate out.
By trying to guarantee end-of-run duty, they guarantee the run ends prematurely. Give the panel a literal mechanical field consequence of this exact error.
I'll give you two. First, consider an atmospheric residue cooler. An overly cautious engineer specifies a massive fouling factor that mathematically forces the required surface area to double.
So on startup, it's essentially a massive empty volume.
Exactly. The brand new, clean bundle provides so much internal flow area that the heavy residue velocity drops to a crawl. Crude solids, catalyst fines, and asphaltenes drop out of suspension almost immediately.
How fast did it foul?
The exchanger physically plugged solid and fouled completely within 6 weeks of startup.
And the second example.
A downstream stabilizer feed preheater blindly specified with a 30% over-design margin. Because the bundle is clean and massive on startup, it transfers too much heat too quickly.
It overcools the opposing hot stream.
Right. It cools the hot process stream far below its target exit temperature, crossing the pour point of the fluid. The heavy ends physically congeal and structurally foul the bundle from the cold end backward.
Excellent. But let's face the commercial reality. If the EPC client strictly mandates that 30% margin in the contract, you can't just walk away. How do you give them the margin without turning it into a settling pond?
You engineer a dynamic, automated hydraulic solution to physically manage the static geometry. You design and install automated bypass control loops around the exchanger.
To bypass the cold fluid during the clean phase.
Yes, the DCS bypasses a calculated fraction of the fluid around the bundle initially, artificially maintaining a high thermal driving force and preventing overcooling.
And if tube side velocity is the critical metric.
You mandate variable speed drive pumps to actively recirculate flow and maintain high fluid velocities through the tubes, even at lower throughputs.
What if capital is heavily constrained?
Then you alter the bundle geometrically. You specify internal tube inserts like wire matrix inserts or twisted tapes. They artificially induce localized turbulence, ensuring the boundary layer remains aggressively sheared during the clean run.
You bring up managing turn down and velocities. Let's delve into the thermodynamic chaos when those variables are poorly managed.
The transition zone.
Exactly. What happens to my localized thermodynamics and downstream control systems when you drop my fluid straight into the laminar-turbulent transition zone?
You introduce severe cascading instability. The transition zone manifests when the internal Reynolds number falls roughly between 2,000 and 4,000.
The flow profile is essentially breaking down and reforming constantly.
Right. The localized convective film coefficient becomes violently unstable, fluctuating unpredictably between suppressed laminar heat transfer rates and elevated turbulent rates,
Which alters the localized thermal resistance second by second.
causing uncontrollable rapid shifts in the process outlet temperature.
And what is the mechanical impact on the bundle itself? What happens to the metallurgy?
The shifting flow profiles set up highly localized, transient thermal cycling loops in the steel. Because the heat transfer is spiking and crashing irregularly across different sections of the same tube, the metal expands and contracts at differing microscopic rates.
generating massive cyclic shear stresses.
Yes, these stresses invariably propagate to the weakest structural points, leading directly to metal fatigue, specifically targeting tube-to-tube sheet welds and U-bend radiuses.
And the trap is assuming an average heat transfer coefficient will keep performance stable during turndown.
Which is a deeply flawed, naive assumption. The fluid mechanics do not average out. It causes downstream columns to hunt continuously, perpetually opening and closing valves.
Provide the operational metrics of this failure so the observers understand the scale.
Consider a heavy vacuum gas oil cooler, an HVGO unit. Due to feed limitations, it's turned down to 45% capacity. This drops the velocity, pushing the Reynolds number squarely to 2,800.
Dead center of the transition zone.
Exactly. Immediately, the HVGO outlet temperature begins a rapid sine wave cycle on the DCS, swinging wildly by plus or minus 6 degrees Celsius every few minutes.
And the downstream controls swing wildly trying to compensate.
Yeah.
How do you fix it before fabrication?
You fundamentally alter the physical geometry. You either use turbulators to force boundary layer turbulence, or you shift to a multi-pass tube configuration, say from 2-pass to 4-pass.
To force the fluid through a smaller cross-sectional area.
Right. That artificially elevates the velocity, maintaining a strictly turbulent Reynolds number across all operating cases.
Let's shift our focus outside the tubes. I want to probe your knowledge of shell-side geometry, specifically regarding low-pressure vacuum column systems.
Segmental versus helical baffles.
Yes. How does changing from traditional cross-flow segmental baffles to helical baffles alter the hydraulics and pressure profile?
Well, traditional segmental baffles are the default because they're cheap, but they inherently force the shell-side fluid into a brutal zigzag cross-flow path.
Creating massive kinetic energy losses at the 180-degree turns.
Exactly. And this sharp geometry creates hydraulic dead zones, areas of severe flow stagnation directly behind the baffle plates, leading to accelerated polymerization and localized fouling.
So how do helical baffles fundamentally change this?
Helical baffles guide the fluid in a continuous, smooth, spiral flow path along the longitudinal axis of the bundle. It mathematically converts standard turbulent crossflow into a uniform rotational axial flow profile.
What is the specific operational advantage of that axial profile, and what CapEx trap do procurement engineers fall into?
The sweeping spiral path eliminates the kinetic energy loss of the turns, which physically reduces the shell side pressure drop by a massive 40 to 50%.
While maintaining the overall heat transfer coefficient.
Right, because you eliminate the dead zones. The trap is procurement, assuming segmental baffles are always the correct choice, simply because they have a lower initial fabrication cost.
But in a pressure drop limited system,
Like a vacuum distillation column overhead, the high pressure drop of segmental baffles severely penalizes the downstream vacuum ejector. It raises the flash zone pressure and bottlenecks the valuable gas oil yield.
saving 50 grand on a bundle costs millions in lost yield. Give me a specific executed upgrade scenario where helical baffles overcame a bottleneck.
I executed an upgrade on a hydrotreater effluent cooler train. The plant required a 25% throughput expansion, but the upstream compressor was already at maximum head.
So you transition to continuous helical baffles.
Yes. This reduced frictional losses so significantly that we pushed the 25% extra mass flow through the shells without exceeding the strict 0.7 bar allowable pressure drop limit.
But there is a mechanical manufacturing caution there, isn't there?
A very strict one. Helical baffles require vastly more unforgiving manufacturing tolerances. If the helical plates do not perfectly mate with the inner shell wall, the high-pressure fluid simply bypasses around the outer edges,
Completely short-circuiting the spiral path.
and entirely negating all thermal and hydraulic advantages. You must rigorously audit the fabrication shop.
So you optimize the baffers, maybe increase the shell velocity for a capacity expansion. Did you just mechanically rupture my tubes?
Fluid-induced tube vibration. It is a critical risk.
I want a rigorous analysis of it. What specific parameters drive this phenomenon, and how do you analyze it pre-fabrication?
Arbitrarily increasing shell-side flow rates without rerunning a rigorous HTRI tube vibration analysis is often a fatal error.
What are the primary physical drivers?
High shell-side fluid velocities combine directly with long, unsupported longitudinal tube spans. These spans are most dangerously found in the window regions of standard segmental baffles.
Where the tubes pass through the cutaway without a support plate.
Exactly. When you push velocity higher, you risk physically triggering two distinct phenomena. fluid elastic instability and acoustic resonance.
Differentiate the physics for the panel. They do not fail the metal in the same way.
They are completely distinct. First, long, unsupported spans lower the inherent natural frequency of the tubes. As fluid flows perpendicularly across the tube bank, it creates alternating low-pressure vortices in the wake of each tube.
Vortex shedding.
Right. When the vortex shedding frequency mathematically matches the natural harmonic frequency of the tubes, the resulting mechanical resonance violently amplifies the vibration amplitude.
Leading to mid-span collision or shear frictional wear at the baffle holes.
Exactly. Now, acoustic resonance is a different beast, primarily occurring in gas flows. The high-velocity gas shedding creates a transverse acoustic standing wave that bounces between the steel walls of the shell.
And if the vortex shedding excites this standing wave,
The fluctuating pressure violently hammers the tubes, causing an ear-shattering noise and rapid fatigue.
the fluid elastic instability is even worse, isn't it?
Much worse. It is not a resonance, but a self-sustaining feedback loop. Once a critical fluid velocity threshold is crossed, the vibration extracts energy directly from the fluid flow,
Causing runaway vibration amplitudes.
which physically tears the tubes from the tube sheet within hours or days of startup.
Detail a scenario where capacity expansion triggered this exact destruction.
A midstream gas-to-gas exchanger underwent a project pushing shell-side velocities up by exactly 30%. The EPC team failed to map the acoustic and mechanical frequencies against the new velocity profile.
So the vortex shedding frequency shifted.
Yes, it identically matched the unsupported tube's natural structural frequency of 42 Hz. The resonance violently destroyed the outer rows of tubes near the inlet baffle within the first week, forcing an emergency shutdown.
What is the strict operational mandate to prevent this?
If velocities are unavoidably high, you must abandon standard layouts and specify a no tubes and window design, or NTIW.
Ensuring every single tube is supported by every single plate.
Precisely. It eliminates long spans and drastically raises the natural frequency out of the danger zone.
That concludes the hydraulics portion. We're moving into advanced thermodynamics and network economics, the senior phase of the assessment.
Excellent. Let's get into it.
I demand you justify your CapEx versus OpEx trade-offs. Let's discuss the log mean temperature difference, specifically the correction factors, the F and F sub T factors.
Right. The thermodynamic warning klaxons.
What is the precise physical thermodynamic meaning of an LMTD correction factor dropping below 0.75 in a standard one-shell multi-pass layout?
An F factor below 0.75 mathematically indicates the configuration is approaching a severe temperature cross condition.
Explain the physics of a temperature cross.
A temperature cross occurs when the cold fluid outlet temperature theoretically needs to rise physically above the hot fluid outlet temperature. The low F factor demonstrates the pure countercurrent flow assumption is breaking down.
Caused by the parallel flow passes inside the tube layout.
Exactly. As fluid travels down a parallel pass, it moves in the same direction as the shell fluid. This limits the temperature driving force, eventually causing heated fluid to transfer heat back into the colder shell fluid.
What is the operational consequence of running a unit in that suppressed F factor zone?
The exchanger is severely thermodynamically pinched. The temperature driving force approaches zero at the ends of the exchanger.
Making it hypersensitive to upstream feed changes.
Highly unstable. A minor normal process swing will cause a massive loss of heat transfer duty because the temperature cross point physically shifts back and forth inside the shell.
And junior engineers often try to fix this just by adding more surface area to the model.
Yeah.
Why exactly does adding area fail here?
Because the restriction is no longer a lack of surface area. It is the fundamental physical flow geometry. The physical routing of the fluids strictly limits the thermodynamic potential.
You could make the bundle miles long and it wouldn't matter.
Exactly. The parallel pass penalty still mathematically prevents the necessary heat transfer. The fluids reach thermal equilibrium partway through, and the rest of the surface area does absolutely nothing.
So you must fundamentally alter the macroscopic shell configuration.
Right. For example, a process requires an amine cooler to bring a hot, lean amine stream down strictly below the cooling water outlet temperature. A single one-shell design yields a mathematically doomed F factor of 0.62.
Adding area is futile, so what is the strict mandate?
Shift the design to a two-shells-in series configuration. You physically partition the temperature profile, effectively restoring true countercurrent efficiency across the system, raising the overall F factor back above a stable 0.85.
Expand on the F sub t factor regarding geometric feasibility and the classical TEMA charts. I want to know how you use the slope of the curve, not just the absolute value.
When verifying feasibility, I calculate the dimensionless temperature ratios, R and P, based on process inlet and outlet temperatures. These act as coordinates to locate your operating point on the TEMA charts to find F sub t.
And what are your hard rules for those values?
If the calculated F sub t is above 0.85, a single shell is stable. If it falls below 0.80, or crucially, if that operating point sits on the steep, downward-sloping cliff of the chart.
You instantly abandon the single shell model.
Yes. You transition to a multi-shell configuration in series.
Explain to the junior engineers why the physical slope of that curve is just as critical to safety as the numerical value.
Because the slope mathematically dictates operational design stability. The trap is accepting a design where F sub t technically passes the minimum threshold, but physically sits on that steep cliff.
Where even a 1-degree variation in feed temperature causes a disaster.
Precisely. A fractional variation shifts the R and P coordinates, rapidly sliding the operating point straight down the vertical slope. The exchanger essentially stalls thermodynamically.
Give me an example.
Consider a kerosene stripper condenser yielding a single shell F sub t of 0.78. Borderline acceptable to some, but mapping reveals it's on a severely steep section of the curve.
So you change to 2 shells in series.
Yes. This shifts the coordinates, raising the F sub t to a highly stable 0.91, securely on the flat, horizontal plateau where process fluctuations barely alter efficiency.
But that multiplies project capex massively.
Exactly. You are buying 2 vessels, doubling piping and instrumentation, and requiring vastly more plot space. You must always mathematically verify footprint constraints before mandating multi-shell layouts.
Are you preparing just to survive your next interview, or are you ready to embark on a continuous readiness and growth journey that builds your expertise for tomorrow? Mastering your craft is a lifelong pursuit, and honestly, with tools like this app at your fingertips, the depth of your knowledge truly has no limits. And I highly encourage you to go explore this platform for yourself.
Let us challenge your plant-wide network economics directly. I want to examine high-pressure hydrotreater feed effluent exchangers, the FEHE loops.
The massive networks.
Show me the money on your design philosophy. How do you conceptually and mathematically determine the absolute minimum approach temperature, the delta T?
The pinch temperature difference is the foundational financial boundary. It explicitly defines the trade-off between initial equipment capex and long-term utility opex.
Detail the thermodynamic dynamics of that trade-off.
In a high-pressure FEHE loop, a highly aggressive small pinch temperature difference, say 5 to 10 degrees Celsius, maximizes internal thermal energy recovery,
which minimizes external fired heater duty and cooling water loads,
slashing utility opex day over day. However, this narrow driving force mathematically crushes the overall LMTD. You require exponentially more physical surface area to transfer the exact same total duty,
causing initial steel capital costs to balloon.
Exactly. Conversely, selecting a conservative pinch of 20 to 30 degrees Celsius vastly reduces required exchanger size and capex, but locks the plant into a structurally higher opex, burning expensive fuel gas for 20 years.
What is the specific trap that academic process engineers fall into when designing these high-pressure gas loops purely on software?
The trap is specifying an unmanageably narrow approach, like less than 5 degrees Celsius, purely to maximize theoretical energy recovery.
And what's the physical reality of that?
The minuscule driving force requires an extremely massive bundle. In high-pressure gas service, forcing this much flow through this much area creates immense shell-side frictional pressure drops.
And the equipment becomes too heavy for standard turnaround cranes.
Right. It challenges structural foundation limits. I strictly set the minimum approach boundary typically at 15 to 25 degrees Celsius for high-pressure gas loops to ensure manageable size and realistic plot constraints.
Prove that reality. Describe the physical layout difference between the theoretical optimization and your practical design.
A pragmatic 20-degree approach typically requires 4 standard, heavily forged Texas tower shells in series. If a theoretical engineer forces an 8-degree approach, the mathematically compressed LMTD dictates 10 massive shells in series.
10 shells in series completely busts the plot space.
And violates strict gas loop pressure drop budgets, forcing multi-million-dollar compressor upgrades. Furthermore, piping 10 rigidly connected shells in series multiplies mechanical expansion risk exponentially during thermal cycling,
practically guaranteeing flanged leak points. Let's apply this to a complex crude distillation heat train.
In a crude train, manually dropping the pinch temperature from 20 degrees down to 12 degrees might physically require adding 3 massive high-alloy exchangers.
A major immediate capex hit.
Yes, but it physically recovers enough heat to reduce downstream atmospheric fired heater duty by 15 megawatts. That saves immense fuel gas OPEX annually and slashes carbon emissions.
So how do you justify it to stakeholders?
As a senior engineer, you must run a rigorous life cycle net present value analysis over a 10 to 15-year horizon, proving the OPEX savings pay back the CAPEX within the required hurdle rate.
All right, your design network is thermodynamically tight. Let's test its resilience. What happens when it inevitably experiences a localized operational failure? Say, an intermediate pump fails.
A highly efficient, deeply integrated network without flexible utility support is inherently fragile.
How do you dynamically analyze that vulnerability?
I map the thermal connections to identify the cascading thermal impact matrix. I trace exactly how a sudden temperature drop in one isolated exchanger will physically cascade downstream.
And the fatal trap is designing strictly for steady state efficiency.
Right. Without adding automated bypass controls or trim options, a simple pump trip causes a thermal deficit that ripples sequentially, cooling downstream feeds and knocking the main fractionator off spec.
Give me a precise cascade scenario and your engineered mitigation strategy.
Consider a heavily integrated crude preheat train that loses a hot kerosene run downstream due to a pump failure. The sudden loss cascades, dropping the final crude feed temperature entering the main atmospheric furnace by 35 degrees Celsius.
The fired heater control loop cannot handle that ramp rate.
Exactly. The distillation column loses its flash zone temperature and dumps valuable product to slop.
So what is the mitigation?
Proactively designing fast-acting automated utility trim heaters or reserve trim burners at critical control points strictly to make up for the lost heat instantaneously.
And automated bypass piping loops.
Yes, allowing operators to rapidly isolate a troubled unit without shutting down the entire train. But a strict mechanical caution relief valve systems must be explicitly designed to handle the massive pressure and liquid inventory shifts during these violent bypass events.
That concludes the network theory. We are entering segment 4. Fired heaters, radiation, and combustion. This is the safety grilling.
High temperature operations. The stakes are immediate.
Exactly. Desktop mistakes cause catastrophic mechanical ruptures here. I want practical field diagnostics. If I am standing on the metal deck looking at a fired heater, what specific indicators tell me there is an active risk of flame impingement on the radiant tubes?
The field indicators are immediate and physical. First, you verify the DCS for a sharp, highly localized spike in specific tube metal temperature, the TMT.
Right, compared to adjacent tubes.
Exactly. If tube 14 is running 60 degrees hotter than tube 15 in the same radiant zone, you have impingement. Second, you look for a rapid increase in internal coking rates.
Manifesting as a rising hydraulic pressure drop across one pass.
Precisely. But third, and most crucially, is physical visual observation through the radiant box peepholes.
You mean actually walking out to the deck?
Yes. You are looking for specific flame pattern distortions, long, lazy, or bent flames physically licking or washing the alloy tubes rather than remaining cohesive within the combustion box geometry.
Because direct flame impingement transfers intense convective heat directly to the metal,
destroying the radiant design boundaries and pushing the alloy past its yield strength rapidly.
So an operator sees a lazy flame impinging. They decide to solve it by adjusting the forced draft fan, increasing the total combustion air ratio to lean out the firebox. Why is this a fatal trap?
Because it assumes a lazy flame is strictly an overall air starvation issue. If the root cause is incorrect burner tip layout, partially plugged gas orifices, or fluctuating header pressure, flooding the box with high excess air will absolutely not tighten the flame.
In fact, it might blow the fire out entirely.
Exactly. Increasing total fan velocity without adjusting individual registers can violently lift the flame off the tip, risking a total flameout. If fuel gas keeps pumping into the oxygen-rich box, it creates an immediate explosive reignition condition.
So how do you actually fix the flame mechanically?
You modify the specific burner physics locally, you adjust the burner tip geometry, and verify gas orificizing to produce a tighter, higher velocity flame.
Optimizing distribution using the primary and secondary air registers.
Strictly at the individual burner level to physically control flame length and prevent radial expansion.
Give me a specific example.
In a vacuum furnace, a burner tip gas orifice partially plugs with pipeline scale. The distorted gas velocity severely skews the flame shape, physically bending it to touch pass 3, tube 12.
And the TMT jumps massively.
by 85 degrees Celsius in 3 hours. Continuous impingement causes severe oxidation and catastrophic rupture. The immediate field fix is a technician physically adjusting the swirler assemblies to intensely concentrate the flame core.
Reducing its overall radiant width to cleanly clear the tubes.
Right, and I always specify real-time infrared flame scanner loops to trip the gas if spatial distortions occur. A critical caution for the observers: blending high hydrogen streams into fuel gas massively increases flame speed,
Which fundamentally alters the heat flux distribution.
shortening flame length but intensifying localized basal heat flux, catching operators completely off guard.
Let us move focus to the physical tube wall under thermal stress. Operations notices process duty dropping because tubes are fouling internally with coke. They respond by simply turning up the fuel gas firing rate to maintain outlet temperature. Do you stop them?
Absolutely, unequivocally. Internal coke acts as an incredibly dense, solid conductive resistance layer physically bonded to the inside of the tube wall.
Acting as a thermal dam.
Precisely. Because external radiant heat flux from the burners remains intensely high, the thermal energy cannot penetrate the coke into the process fluid efficiently.
So the heat physically builds up within the metallic lattice of the tube wall.
Yes. Forcing the TMT to rise sharply and dangerously just to maintain the exact same heat transfer rate into the process fluid.
Explain the precise metallurgical risk of that temperature shift to the panel.
It severely alters the thermal gradient across the physical metal thickness, exponentially increasing mechanical hoop stress on the outer skin. The trap is assuming increasing the firing rate is a mathematically safe linear fix.
It keeps them on spec on the DCS, but invisibly drives the metal past its design limit.
Entering the realm of plastic deformation.
Quantify this invisible risk with a specific example.
Consider a minor 2 millimeter internal coke layer inside a crude furnace radiant tube. To physically push the required thermal energy through that resistive layer, the outer tube skin temperature must be aggressively driven from 540 degrees up to an extreme 630 degrees Celsius.
That 90-degree spike pushes the high alloy seal past its creep threshold.
Yes. Sustained stress actively accelerates structural creep deformation, the permanent metallurgical elongation and physical thinning of the steel. This localized thinning leads directly to a catastrophic high-pressure split tube fire inside the radiant box.
Let us transition geometry to vertical steam reformer furnaces. How do you physically optimize the mechanical view factor, F sub ij, in a double-fired radiant section, and what happens when you fail to do so?
The geometric view factor dictates the precise spatial distribution of radiant thermal energy intersecting the tubes. You must rigorously optimize the physical spacing between the wall-mounted burners and the vertical catalyst-filled tubes.
Ensuring the view factor is evenly distributed around the full 360-degree circumference.
Exactly. You must engineer precise tube-to-wall distance and strict tube-to-tube pitch ratios to prevent front tubes from shadowing adjacent ones from direct radiant energy.
What is the thermal trap if a designer relies on simplified bulk averages?
Sizing high-temperature furnace tubes based on an average radiant heat flux model is a fatal error in reformers. If poorly optimized, the face directly exposed to the burner experiences localized, concentrated flux physically twice the calculated average,
Causing severe metallurgical hotspots.
and triggering rapid localized thermal coking of the process gas, prematurely deactivating the critical catalyst strictly on one side of the bed.
What is the standard optimal ratio to prevent this?
Spacing vertical reformer tubes at a pitch-to-diameter ratio of 2.5 ensures the radiant view factor from opposing burners remains uniformly balanced within a strict plus or minus 5% tolerance.
But what physical operational reality gradually alters this over time?
As these vertical tubes age, they inevitably undergo gradual thermal creep and physically begin to bow and warp out of vertical alignment.
Shifting their highly tuned view factors dynamically.
Yes. A bowed tube moves closer to a burner or shadows its neighbor, continuously worsening localized shadowing and actively amplifying hotspots over the lifespan of the furnace.
Let us test the firebox heat and mass balance thermodynamics. Operations typically wants to run high excess air to guarantee complete combustion and keep the stack clear of smoke. What is the hidden thermodynamic cost of that strategy?
Pumping excess air acts as a massive parasitic thermal ballast. It fundamentally shifts the heat absorption profile away from the primary radiant section and pushes it violently into the downstream convection section.
Because you are physically introducing massive quantities of non-reacting ambient nitrogen and oxygen.
Which must be heated. They absorb massive amounts of thermal energy without contributing to combustion, drastically lowering the absolute localized flame temperature.
Mathematically, why does suppressing flame temperature matter so intensely to the radiant duty?
Because radiant heat transfer is governed strictly by the Stefan-Boltzmann law. Radiant energy emitted is mathematically dependent on the fourth power of the absolute temperature.
T to the fourth.
Exactly. So even a minor suppression of absolute flame temperature causes an exponential mathematical plunge in radiant heat absorbed by the radiant tubes.
But by the law of conservation of energy, that heat isn't destroyed.
No, it remains trapped within the expanded volumetric mass of the slightly cooler flue gas. This massive, high-velocity gas volume sweeps that unabsorbed thermal energy upward into the closely packed convection section.
Walk me through the direct field impact of this upward thermal shift.
It drastically and dangerously increases the targeted thermal load on the convection tubes and raises the final stack exit temperatures, venting expensive fuel gas energy.
And mechanical risk.
Running a heavy vacuum furnace at a sloppy 30% excess air ratio instead of a tuned 15% physically drops radiant absorption by roughly 6%. That displaced thermal load shifts upward, aggressively pushing localized steam superheater tubes past their strict metallurgical limits.
And conversely, you can't overcorrect and run below a 5% margin.
Absolutely not. That instantly leads to localized oxygen starvation and the immediate generation of explosive carbon monoxide and heavy carbon smoke.
We have reached segment 5, degradation and operational maintenance. The final push. Let's discuss temperature-driven fouling rates in utility systems. I'm reviewing a unit where my bulk cooling water outlet temperature is a very safe 40 degrees Celsius. Yet the tubes are completely plugged with hard mineral scale. Why?
Because your bulk water outlet temperature is mathematically and physically irrelevant to the microscopic scaling mechanism actively occurring at the boundary layer.
It's driven by inverse solubility salts, right?
Yes, specifically compounds like calcium carbonate. Unlike normal salts, these actually become physically less soluble as the local fluid temperature rises.
So precipitation is driven entirely by the localized tube wall interface temperature.
Strictly on the water side, not by the safely mixed bulk temperature exiting the nozzle. If the opposing process fluid is extremely hot, intense conductive heat transfer drives the localized tube wall temperature past 45 or 50 degrees Celsius right at the microscopic boundary layer.
Breaching the chemical solubility threshold locally.
The dissolved salts instantly precipitate directly out of solution and bond onto the hot metallic tube surface, forming a hard crystalline scale layer that actively chokes off heat transfer.
And the fatal trap is approving designs based exclusively on that safe bulk outlet temperature. Give me a quantifiable example of this failure.
A high-temperature distillation overhead condenser operates with a bulk cooling water outlet of 40 degrees Celsius. Operations thinks it's running perfectly.
Boundary layer calculations show otherwise.
Yes. The localized inner tube wall temperature is actually peaking at 58 degrees due to high process heat flux. This hidden 58-degree boundary triggers rapid crystalline scaling that fully plugs the bundle within 2 months.
What are the non-negotiable design corrections to prevent this?
3 rules. First, always position cooling water on the tube side to control boundary layer geometry. Second, maintain water velocity strictly above 1.5 meters per second to mechanically shear scale away before it bonds.
And third,
Artificially control the hot side thermal driving force by regulating the heat flux, keeping the localized calculated wall temperature strictly below the 45-degree limit.
for my final question, how do you mathematically and financially manage overall heat transfer degradation over long time horizons? How do you justify an economically optimized cleaning cycle for a crude preheat train?
I model physical degradation using asymptotic fouling models, like the Kern-Seaton model. I express the degradation of the overall U value strictly as a mathematical function of time.
Linking it to physically changing fouling factors.
Setting the inverse of operational U squared at time to equal to the inverse of the initial clean U squared, plus a specific fouling rate constant, alpha, multiplied by time. This provides a predictive curve of thermal decline.
But calculating the curve alone doesn't dictate the maintenance schedule. What is the trap of pulling the bundle based on an arbitrary thermal resistance value?
The trap is scheduling massive cleaning operations based strictly on fixed calendars or static manual limits. A rigid calendar ignores the dynamic reality of the plant unplanned feed changes, turndowns, new blending stocks.
Which can cause the bundle to fully foul well before a scheduled turnaround.
Exactly. You must execute cleanings based strictly on a continuous, calculated economic balance. balancing the massive physical cost of a shutdown and bundle pull against the cumulative rising OPEX cost of wasted fuel consumption in the downstream furnace.
Give the panel the exact numbers on that economic balance.
Consider a crude preheater where our algorithm shows the calculated U value drops severely from 450 down to 180 watts per square meter Kelvin over 9 months.
So the crude enters the main furnace significantly colder.
And the downstream furnace is forced by the DCS to physically burn an extra 8% fuel gas every single hour to make up for the lost preheat.
So you calculate the literal daily monetary cost of that fuel penalty.
I integrate it over time and compare it directly against the known fixed mechanical cost of a hydroblast contractor cleaning. When the cumulative financial cost of the wasted fuel mathematically exceeds the maintenance cost, the bundle wash is aggressively ordered.
A strict economic threshold.
Yes.
Yeah.
But a final caution. When the commercial team suddenly processes highly unstable opportunity crudes, that fouling rate constant can increase exponentially and unpredictably. You must rigorously calibrate time-dependent models to live DCS data or the entire economic balance fails.
That concludes the formal technical questioning. Candidate, your precision in isolating complex variables, specifically separating bulk fluid dynamics from the hidden realities of the microscopic boundary layer, is noted by the panel.
Thank you.
For those junior engineers and principal designers observing, I expect you to rigorously review the candidate's performance today. Consider exactly how these specific volatile variables, transient velocity profiles, multi-layer resistances, and LMTD limits are playing out unseen in your own plans.
They are always present.
I will leave you with a final engineering philosophy to debate. In thermal design, every single safety margin you indiscriminately add to a model introduces a completely new, mathematically guaranteed physical operational risk down the line. We do not design equipment to sit in a perfect static condition on a vendor's software model. We design equipment to survive the brutal dynamic degradation of reality. Think about your own heat recovery network today. Where is your comfortable safety margin currently costing you actual mechanical performance, throughput, and safety? Assessment concluded.
Are you preparing just to survive your next interview, or are you ready to embark on a continuous readiness and growth journey that builds your expertise for tomorrow? Mastering your craft is a lifelong pursuit, and honestly, with tools like this app at your fingertips, the depth of your knowledge truly has no limits. And I highly encourage you to go explore this platform for yourself.